Today I'd like to talk to you about vector forms of Green's theorem. We'll do one in particular, and in a second lesson we'll do another. Okay, so let's remind yourselves what Green's theorem says. It says that the line integral around the closed curve C, f dot dr, is equal to this, p dx plus q dy. Well, actually, that's just a line integral. That's not what Green's theorem says. But we're going to start here, and we're going to land in an interesting place. All right, let's remind ourselves what curl is for a moment. All right, so curl of f is equal to this determinant, I, j, k, and it's the determinant between the cross product between the gradient operator and the components of the vector function. So this is a component, this vector function just has two components, p of xy, q of xy, and then it doesn't come out of the xy plane or doesn't move in a third dimension, so that third component is 0. Okay, so let's do the calculation here and see what we notice. Something pretty neat happens, actually. So let's do that. So what do we get? We get I times its minor, which would be partial y, partial z, q, and 0. Okay, well, let's keep it. Actually, I'm going to put the x comma y here to remind you of something. All right, so then we're going to have, let's not lose track of this, and you have minus j. Don't forget that plus minus plus business you got to do. You expand by a row to get a determinant. Minus j times its minor, so that's going to be partial x, partial z. And here you have p of x comma y, and then 0. And then lastly, you have plus k times its minor, which is partial, just in case you don't see that, it's right here. Here's the minor of k. Right? So it's partial x, partial y, and then you have p of x comma y and q of x comma y. And watch what happens. Very nice thing. So let's look at this first piece for a second. You have the partial derivative with respect to y of 0. That's clearly 0. Okay? Minus the partial derivative with respect to z of the function q of x comma y. Now, the notation q of x comma y is telling us that q is only a function of x and y, and we're trying to take the derivative of that thing with respect to z. So that would have to be 0, because it doesn't have any z variables in it. Okay? So there you go. That's sort of nice. Let's see if anything else happens that's sort of clean like that. All right, so minus, oops, hold on a second, minus j times, and let's just move up a little bit here, minus j times, now look what happens again. Derivative of that thing with respect to x of 0 is going to be 0. And the derivative with respect to z of the function p of x comma y, but p of x comma y is only a function of x and y, not z. So its partial derivative would also be 0, so that's 0, 0. All right, good. Plus, lastly, k, and get ready for something pretty familiar. The partial derivative of q with respect to x, so it's partial q, partial x, minus the partial derivative with respect to y of p, so partial p, partial y, times k. So now if you look at that, that's sort of interesting. That actually looks like something we've seen before. It looks like the thing we take the double integral of in Green's theorem. Okay, so let's look at one more interesting expression. Consider this. Suppose I take the curl of f, which we just found, okay, and we dot it with k. Now remember, f is a function, f of x comma y is equal to p of x comma y I plus q of x comma y j. So that's it. There's only two components. All right, it doesn't move up in a third dimension here. So let's consider this expression. Well, we would know that this is equal to partial q partial x minus partial p partial y k dot k. All right. So what do we know about finding dot products of vectors? Well, think about what these two vectors look like. The first vector looks like this, 0, 0, and then partial q partial x minus partial p partial y. Sometimes it's just easier to write this out. If you see this right away, then I'm sorry if you haven't to watch this. Dotted with the vector 0, 0, 1. is just the scalar quantity, partial q partial x minus partial p partial y. Okay, so what does that tell us? It tells us we can write Green's theorem in a slightly different way. We can say that the line integral of f dot dr, which also can be written as the line integral around c of p dx plus q dy, is just equal to the double integral of the curl of f dot k dA. So this equation here, if we take a careful look at this and what this is telling us, sort of a fun thing. This is saying that the line integral of the tangential component along f, don't forget what this is doing. This is telling me the line integral of the tangential component along f. We've talked about line integrals around curves. So you're moving around here. This is your closed curve C. And what we've done is, if you think about the expression f dot dr, right, that's a dot product, right? That's sort of a special thing. What we said was is that that sort of adds up all the work done in the direction of the tangent vector as you move along this curve, okay? So that integral of all that work together, okay, from start to finish, is equal to the double integral of the vertical component of the curl over the region D. So that sounds like a lot of words, but if you think about what this is, the curl of f has a component horizontally, has a component vertically, and has a component coming off the board at you. So every point in here has a component of curl that comes up out of the board. And I say comes up out of the board because remember, we're only dealing with a vector function that has two components. It moves horizontally and vertically. And then there's this third component we can consider for curl that comes up out of the board. And this is saying that all the work done to get around the boundary of region D is the same as the sum of all these vertical components of the curl that come up out of the board at you. So this is a fun little fact. Okay? All right. In the next lesson, what we'll do instead is we'll talk about this. We'll talk about a way to relate these things or drive a similar formula that has to do with the normal component of f as we move around this curve and its relationship to the area on the inside and what sort of fun fact we get there. Okay? Thanks for watching.